Okay, before I move on to solving the second problem, let me just prove the relation between the acceleration in the primed frame and acceleration in the unprimed frame in a somewhat different way. Uh, we had found out that the relation between the velocity in the primed frame and velocity in the unprimed frame is given by v prime vector equals to v vector minus omega vector cross r vector. Actually, we had written it in a different way. It was v vector equals to v prime vector plus omega cross r vector, but this is just as good. Let me first derive this in a almost similar manner. I know I'm being a little pedantic, but please bear with me for a while. Say I differentiate the position vector as seen in the unprimed reference frame with respect to the unprimed reference frame. Now, because r and r primed are equal, let me just write out r vector as r primed vector. So let me just write out the expansion of r primed vector. By expansion I mean the components along with the unit vectors plus y primed j primed cap plus z primed k primed cap. Now this differentiation is being done in the unprimed frame of reference. So this becomes x primed d I cap primed over dt, the differentiation being done in the unprimed frame of reference, y primed d j cap primed over dt sigma plus z primed d k cap primed over dt sigma plus I cap primed dx primed over dt, this differentiation too being done from the unprimed frame of reference, j cap primed dy primed over dt sigma plus k cap primed dz primed over dt sigma. Now we had shown that this is equals to omega cross I primed. How had we shown that? We had shown that that if some vector given by r, if it is constant in the primed frame of reference, from the unprimed frame of reference, its tip or the vector itself seems to move or rotate with angular velocity omega, the angular velocity of the primed frame of reference. So the velocity or the time derivative of this vector, the time derivative being done in the unprimed frame of reference, is just omega cross r. And because r and r primed are equal, I can just as well write r primed here. This formula, so this is just basically r primed vector dot just means dr vector or r primed vector over dt, the differentiation being done in the unprimed frame of reference. So in this formula we just have to remember that r primed vector is a vector that is constant or stationary as seen from the primed frame of reference, and as seen from the unprimed frame of reference it seems to move with angular velocity omega, that is the angular velocity of the primed reference frame. So because I primed, j primed and k primed, all these vectors are constant as seen from the primed frame of reference, this formula holds for these vectors. So it becomes this simply becomes x primed times omega cross I primed. This term will become omega cross j primed, this term will become omega cross k primed. So we just have omega cross r primed vector, and in these differentiations we are basically only differentiating scalar functions of time, and for scalar quantities it does not depend from which reference frame I am differentiating. So I can just as well differentiate these from the primed reference frame. So this just becomes the derivative of the x primed coordinate, which is a function of time, as seen from the primed reference frame. So this is just the x component of velocity as seen from the primed reference frame, and similarly for these. So this whole expression just simply becomes the v primed vector, and dr by dt as done from the sigma frame is just the v vector. So we get back to this formula, and now just for fun, let me differentiate the v primed vector with respect to time as seen from the sigma or the unprimed frame of reference. Now if I write out the v primed vector, it is just I primed cap vx primed plus j primed cap vy primed plus k cap primed vz primed. The entire derivative will have to be done from the sigma reference frame. Now this is just in the same way as this, we can write it out: vx primed d dt of I cap primed. By the way, if I differentiate with respect to time I primed cap, but I differentiate it from the primed reference frame, these terms will go to 0. That is, d I cap primed over dt as done from the primed reference frame will just be 0, and so will these quantities be also 0, because from the primed reference frame I cap primed, j cap primed and k cap primed, they're all constant vectors. So getting back here, vy primed d j cap primed over dt plus vz primed d k cap primed over dt. We have more terms: I cap primed d vx primed over dt as done in the sigma frame. All these are also done in the sigma frame, plus j cap primed d vy primed over dt sigma plus k cap primed d vz primed over dt as done in the sigma frame. So the combination of the first three terms, these terms, they will give us vx primed times omega cross I cap primed. Similarly for these, so I get omega cross v primed. This arises from the first three terms. For the next three terms, I am again differentiating only scalar quantities, scalar functions of time. So it doesn't matter from which reference frame I differentiate them. So let me differentiate them from the primed reference frame. So we shall see this is just the x component of acceleration as seen in the primed reference frame, y component of acceleration as seen in the primed reference frame. This is the z component of acceleration as seen in the primed reference frame. So this just becomes a primed. Now we also know that v primed vector equals to v minus omega cross r. So if I substitute v minus omega cross r in place of this, I shall get an a vector, and differentiating this with respect to time as seen from the unprimed reference frame, I shall get minus omega cross v, and the other term will be minus d omega by dt as done from the sigma reference frame cross r. So this, this is just equal to this because both have come from here. So if I equate them, so we have this equals to this, and therefore we can write A vector minus omega cross V. In place of V, let me substitute V prime, plus omega cross R minus d omega by dt as seen from sigma, or we can just leave it as d omega by dt, because it doesn't matter from which frame I differentiate omega. This will be equals to omega cross V prime plus A vector. So let me just leave, sorry, A prime vector. Let me just leave A vector here and bring the rest of the terms to this side. Then I shall get minus omega cross V prime plus omega cross V prime. I'm bringing this minus omega cross V prime to that side, so I shall get twice omega cross V prime. I shall get a plus omega cross R, and I shall get a plus d omega over dt cross R. So I'm back to the same expression. I've gone over it a little fast, a little bit faster than I should have perhaps, but I hope I've made my point. So let me just move ahead to the problem. Suppose we are given a horizontal disk which is rotating with angular velocity omega, and this is my y-axis, this is my x-axis, and we are given a groove on which a particle is lightly placed at a distance y from the y-axis, sorry, at a distance b from the y-axis, and they are asking us to find the position of this particle as a function of time. So we know that two forces will be acting on this particle. If we want to describe the particle from the rotating frame of reference, one of those forces will be the centrifugal force, and the other force, which will act in the downward direction along the negative y-axis, as we shall shortly show, is the Coriolis force. At first, when this object starts to slide along the x-axis, because of the centrifugal force, it gains a velocity, and because it gains a velocity with respect to the rotating frame, therefore a Coriolis force acts on it, and the direction of Coriolis force, or the formula for Coriolis force, is minus of 2m omega cross v. So omega being in the upward direction, and the relative velocity, the velocity of the particle relative to the rotating frame being in this direction, omega cross v will give us the upward direction, but because of the minus sign, the force will be in the downward direction. So first, let us find out what the centrifugal force is. The formula for the centrifugal force is minus m omega cross r. So we can say that the centrifugal force is minus m omega k cap, because the angular velocity being anti-clockwise is in the upward direction, that is along the positive z axis, cross omega k cap cross x I cap. At some instant of time, the particle, say its coordinate is x coordinate is x, y coordinate is obviously 0, because the particle is constrained to move only along the x-axis because of the groove. So this is minus m omega square k cap. Now what is k cross I? So let me just find that out. K cross I is equals to J. So this becomes K cap cross J cap, but K cap cross J cap is minus I, so the centrifugal force simply becomes m omega squared x, I've missed an x I cap. So that is our centrifugal force. What is our Coriolis force? Coriolis force is given by this formula, where v is the relative velocity of the particle with respect to the rotating frame. So this is minus 2m omega k cap cross v I cap. So this is just minus twice m omega v k cross I is just j. So this is just minus 2m omega v j cap. So the Coriolis force, the magnitude of the Coriolis force is this, and it acts in the along the negative y-axis. So the force that the Coriolis force applies on the groove applies that force back on the particle, and that force becomes our normal reaction, and normal reaction balances the Coriolis force. So the Coriolis force acting on the particle in turn acts on the walls of the groove, and the groove pushes the particle back in the opposite direction by Newton's third law. And the normal reaction just balances the Coriolis force. That's a bit of a bummer, because the Coriolis force is cancelled out. It will no longer play any role in the rest of the problem. So only the centrifugal forces has any bearing on the motion of the particle. So the acceleration then, only this force being the significant force, the acceleration of the particle is just omega squared x. Let me just say that the magnitude of the acceleration is omega squared x. Now this is almost like the formula for acceleration for a simple harmonic motion, where we have a negative sign. We can just do that analysis if we assume another omega, which is omega primed, which is a complex number, which is I times omega. So we know the solution to this equation. The solution to this equation is x equals to a e to the power of I omega primed t plus b e to the power of minus I omega primed t, where omega primed is just I omega. So I am writing the solution to the equation a equals to minus omega primed squared x. Now omega primed being equals to I omega, we can say that x equals to a e to the power of, if I substitute I omega, I get a minus t here, minus omega t here, and plus b e to the power of, if I substitute I omega in place of omega prime here, minus I times I will give me just plus 1, so b e to the power of omega t. If I do the first derivative with respect to time, I shall get minus omega a e to the power of minus omega t plus omega b e to the power of omega t. Now we find out a and b from the initial conditions. The first initial condition is that when time is 0, x is just b. So if I substitute b in place of x and 0 in place of time, I get a plus b equals to small b. If I substitute, okay, in the problem they have said that the particle has been put lightly on the groove at the initial moment at time t equals to 0. So we can assume that at time t equals to 0, the velocity is 0. So if I substitute 0 in place of v, I shall get 0 equals to, and 0 in place of t, I shall get minus omega a plus omega b, which will give me a plus b equals to 0, which will give me a equals to b by 2. So the solution, final solution to my equation will be x equals to b over 2 e to the power of minus omega t plus e to the power of plus omega t. This is my final answer.